This is part B of the section on the introduction to trigonometry with using angles. And here we are going to do some applications. We learned that the definition of the radian measure is that an angle theta in radians will be the length of the arc that subtends on the circle through that central angle divided by the length of the radius. And now if we solve that equation for S, we will find the length of the arc intercepted by the central angle theta, theta being in radians. So we want to use that formula. And again, I want to remind you that this is in our formula packet. On the first page of the pre-calculus formulas, second page of the packet, and we will be working with these formulas in this video. So a circle has a radius of 9.5 centimeters. Find the length of the arc intercepted by a central angle of 120 degrees. So S will equal to R, 9.5 centimeters, times theta in radians. Remember, if you have an angle of 120 degrees and you want to convert to radians, you have to multiply by pi and divide by 180 degrees. You could also remember that 120 degrees is 2 times 60, and 60 is pi thirds. So you could directly write it in terms of radians. You can also look in the formula packet where 120 degrees is one of the listed angles, and the answer would be 2 pi thirds. So I have here 9.5 times 2 pi thirds centimeters. If the problem asks you to write the exact answer before you round to 2 decimal places, actually it does. It says express the arc length in terms of pi, then round your answer to 2 decimal places. I want to go in my calculator and do the math with everything but pi. So 9.5 times 2 and divide by 3. This is the answer. I need to convert it to a fraction. So 19 over 3. So the answer will be 19 over 3 pi centimeters. That's the exact answer. And now I'm going to multiply by pi and round to 2 decimal places. So the answer will be 19.90 centimeters. If the radius of the Earth is 3,960 miles, what is the distance from the equator to a point that is 40 degrees north? So again, that will be an arc's length on a circle, assuming that this is a sphere. It's not really a sphere, the Earth, but close enough for our purposes. The angle of 40 degrees needs to be converted to radians times pi and divide by 180 degrees. The degrees will go away. The answer will be in pi. In miles, I meant. So I'm going to do the math without pi first. 3960 times 40 and divide by 180. 880 pi measured in miles. And then let's multiply by pi and let's round to the nearest mile. So times pi and to the nearest mile, 2,765. The area of a sector is found as 1/2 theta r squared, with theta being the angle intercepting the sector, the central angle intercepting the sector in radians. So a sector is the area of the intersection of an interior of a circle and a central angle. The area of the sector is proportional to the measure of the angle. Pi r squared is the angle of the whole circle. 2 pi is the angle of the whole circle. And therefore, for a random angle theta, the area A will equal to 1/2 theta r squared if I solve this proportion. So here is an example. In a center pivot irrigation system, a large irrigation pipe on wheels rotates around the center point. If the irrigation pipe is 450 meters long, let me get us a color that we can see. Okay, so this is the center, this is the pipe. It is 450 meters and it rotates around this plot, and we want to find how much area can be irrigated after a rotation of 240 degrees. So let's assume that it rotates in this direction. 240 is a convex angle, is more than 180. So let's assume that this is 240 degrees. They're asking us to find the area of this sector over here. So per the formula, the area will be 1/2 theta, 240 degrees times pi divided by 180 times r squared, 450 meters squared. The degrees are simplified. The units that are remaining are square meters, which are good units for area. I'm going to do first the rational part and express my answer in terms of pi. So I'm going to do 1/2 times 240 divide by 180 times 450 squared. And the answer is 135,000. 135,000 pi. The units are square meters. And now I'm going to round to the nearest 1 square meter. So let's say they are not telling me. I do have a comment here. Actually, if they don't tell us what is the customary place to round, if they don't tell us where to round, it is customary to round one additional decimal place than what the values are given as. And in this case, the values are given as whole numbers, so it is customary to round to the nearest tenth. But for our purposes, let's round to the nearest whole. This is 424,115 square meters, so approximately 414,115, 424. Oh, 424, 115 square meters. The last application for the introduction to angles is angular and linear velocity. As a point moves along a circle of radius r, its angular velocity, omega, is the angle of rotation per unit of time. Now, the linear velocity is the distance you cover over time. So we do know that velocity is s over t. S would be the arc covered on the circle that a point is on. The omega, which is the angular velocity, will be theta over t. Now, we do know the formula that S equals R theta, if you remember that. So therefore, if I replace S with R theta divided by T in this formula, then theta divided by T will be the omega. So I will have here that is equal to R times omega. So we have the formula that converts linear speed from angular speed. And of course, it depends on how far from the center you are. Think about it, right? If I have the irrigation system that we saw earlier, a point that is very close to the center, if this is the center, a point close to the center covers a smaller circle and a smaller distance than a point that is away from the center. So your distance from the center will make you go faster or slower depending on how far you are from the center. So your linear speed, it has to be depending on the radius times the angle that you are, the angular velocity that you are, that you have. So let's solve a problem that involves a lot of transformations in ratios. A tire has a radius of 9 inches and is spinning at 80 revolutions per minute. This is one ratio. I do want to draw your attention to another ratio that you should know, that you should generate yourself, and that is that one revolution is the same with 2 pi radians. So find the angular speed of the tire in radians per minute. So if the we know that we are spinning with 80 revolutions in 1 minute, and I want to convert the revolutions to radians, I'm going to say that one revolution is 2 pi radians. Now notice here that I multiplied with the ratio in a way that the revolutions are simplified. And also I want you to remember that radians is not a unit, but it's actually just a placeholder. So I have 80 times 2 pi divided by 1. So the answer here will be 160 pi radians per minute will be my angular speed. So we want to find the speed of the tire in inches per minute and then in miles per hour. So the tire has a radius of 9 inches, and the outside of the tire is the part of the tire that touches the road. So that's the part that determines the speed of the car, or even of the tire, the linear speed. So the linear speed will be omega times r. My omega is 160 pi. The units are radians in 1 minute. And times r, the r is 9 inches. And if you pay attention here, since the radians is not a unit, then if I do the math here as is, I will end up with some number of inches per minute. So inches per minute is the correct unit for what they are asking me to find the speed in inches per minute. So I'm good to go. I'll just do the math. How much is 160 times 9 divided by 1? Is 1440 inches per minute. Now, if I want to know approximately how much that is, since pi doesn't say much, if I multiply this by pi, I will get, this is approximately 45 24 inches per minute. 4,524 inches per minute. That's approximately how much that is. I don't care for that intermediate answer to be in a decimal form or in rounded in any way. I just want the exact answer of 1440 pi inches per minute because I want to find the speed in miles per hour. Now, the way I convert is using ratios. Another ratio that I'm going to need to know is that there are, let me change this to black. All right, there are 12 inches in 1 foot, and also there are 5,280 feet in 1 mile. I also need to remember that there are 60 minutes in 1 hour. I'm going to use these conversion ratios to do dimensional analysis and convert inches per minute to miles per hour. So the way I'm going to do that is I'm going to start with 1440 pi inches in 1 minute. And I want to get rid of inches in the numerator and minutes in the denominator. So I'm going to multiply by inches in the denominator and feet in the numerator. So that ratio, and there is 12 inches in 1 foot, that will get rid of the inches. To get rid of the feet, I'm gonna do the 5,280 feet in the denominator times 1 mile over 1 mile in the numerator. That will get rid of the feet. Now I still have the minutes. So to eliminate the minutes, I'm gonna do 60 minutes. Minutes have to go in the numerator to cancel with minutes in the denominator in 1 hour. I am now in the desired units. I have miles in the numerator per hours in the denominator. And the only thing I'm going to do is that math. So the math is 1440. Remember, I'm not going to use the pi yet. I'm going to leave the pi. I have to remember that it is in the numerator. Divided by 1 times 1 divided by 12 times 1 divide by 5,280 times 60 and divide by 1. So the math is this number. Let's convert to a fraction, 15 over 11. So let's write in red. This is 15 over 11 pi miles per hour. And now I'm going to multiply by pi, and then let's round to the nearest hundredth. So 15/11 times pi. And to the nearest hundred is 4.28 miles per hour. This concludes our applications of angles.